Today we're going to be looking and thinking about parallel circuits and how current moves through a parallel circuit and how voltage acts in a parallel circuit. So here we have a parallel circuit. What defines it and what makes it a parallel circuit is the fact that there is more than one path around the circuit between the positive and the negative poles. And so you can see as current leaves this pole and travels around, well, it could go through branch number 1 and back around to the negative pole, or it could go through branch number 2 and back around to the negative pole. So since there is more than one complete path that the current could follow, that constitutes a parallel circuit. And so that's how we know that it's parallel, since there's more than one path. Let's think about how current would act in a parallel circuit. To begin with, we know that a certain amount of current will be leaving the battery or leaving the voltage source, and will be traveling through this first part of the conducting path. Now, once it arrives at this point, though, it's going to have to divide. You see that at this point we have two paths that it can follow, and so it could travel upward through branch number 1, or it could travel downwards through branch number 2. But it cannot travel through both at the same. That is to say that the full current cannot travel through both branches of the circuit. Current is a physical thing, much like if you were to think of water in a river. If you have a certain amount of water that's flowing down a river and then that river branches, well, all of that water is going to have to either flow down one branch or the other. And in fact, the total amount will flow down one of the two branches. So the total amount of water in the two branches would actually be the same as you originally had in the one. And that's the same for electrical current. However much current is flowing through this portion of the circuit, it'll have to divide, and some will go into this branch and some will go into that branch. Does it have to divide evenly? Well, no, it doesn't. If the resistance of the branches were the same, then it would divide evenly. In this case, you see that it's not. R1 has a resistance of 40 ohms, and R2 has a resistance of 10 ohms. And so clearly R2 has less resistance, and so R2 will be getting more current. So there will actually be a greater amount of current in this branch than there will be in R1. However, the sum of the current in R2 and R1 would add up to whatever the current was before. So if we had a certain amount of current here, let's just say a value I, and in this portion of the circuit it's I1, and in this portion of the circuit it's I2, we could say that the total amount of current I is equal to the sum of I1 plus I2. And so the values there will total up to the amount. And then once they come back together here at the junction on the back side of the branch, then once again we'll have the total amount I again, and so they will come back together just as if a river had split and, say, gone around a small island and then come back together a little further downstream. All right, and then that amount will continue on around. And so that's what's going to happen with current. We can see that current is going to travel through the circuit, divide into the two branches, and then come back together and continue on. Now, in order to know how much current is actually going to leave and ultimately return to the voltage source, we need to be able to apply Ohm's law to the entire circuit. And so we'll do that. We'll say that V equals I times R. Now, since we're applying Ohm's law to the entire circuit, we need to be using the voltage for the whole circuit, which is listed as 12, and we need to be using the resistance for the whole circuit. In other words, the equivalent resistance. So if we were to replace these two resistors with one single resistor, what one single resistor would have the same effect as both of these in parallel? And that's what we mean when we say an equivalent resistance or an equivalent resistor. So we need to find what the equivalent resistor, or Req, is for a parallel branch. The way that that's done in parallel is we take the inverse of Req, and that is equal to the inverse of R1 plus the inverse of R2. And of course, if there were more resistors in parallel, then we would just continue to add the inverse of them on as well. So 1 over Req equals 1 over R1 plus 1 over R2. All right, in this case, 1 over Req, R1 is listed as 40 ohms, so we'll say 1 over 40. and R2 is 10 ohms, so 1 over 10. All right, now in order to add fractions, remember we'll need a common denominator, and it looks like that's going to be 40 for this pair. So 1 over 40 plus 4 over 40, again multiplying 10 times 4 to get 40, so 1 times 4 to get 4. And then when we add those together, 1/40th and 4/40ths will make a total of 5/40ths. At this point, many students like to stop and say, okay, so RAQ is equal to 5/40ths. No, it is not. The inverse of RAQ is equal to 5/40ths. And so at this point, we need to invert both sides of our equation. And so in order to get REQ, that's actually equal to 40/5, which then reducing that is going to be 8. And the unit for resistance is ohms. So at this point, we see that RAQ is actually equal to 8 ohms. All right, well, with a voltage of 12 and solving for the current for the whole circuit, and RAQ of 8, well, 12 divided by 8 is going to give us 1.5. So the current is equal to 1.5 amperes, or 1.5 amps, because amperes are the unit for current. All right, well, at this point, we've discovered that there will, in fact, be 1.5 amps of current leaving and then eventually returning to our voltage source. But then what's going to happen once it gets up here? Well, some of it will divide and go through branch 1, and some of it will divide and go through branch 2. How much in each one? Well, what we need to do in that case then is we need to apply Ohm's law to each individual branch. And so V1 will equal I1 times R1, and V2 will equal I2 times R2. All right. And again, we're solving for I1, and resistance 1 is 40. Let's see if we can improve our time signal. Oh my goodness! Let's see if we can improve any of this. Hey, how about parenthesis instead? See if that works. Great. So 40I is equal to our voltage. But what do we put in for voltage? What's the voltage across this part of the branch? Well, at this point, we need to consider how voltage interacts in our parallel circuit. Remember that since this is a 12-volt source, that means that we have 12 volts of potential on this side of the source and 0 at this point. So we have a 12-volt potential difference between the terminals, or between the poles. The only time that voltage is used is when current is actually moved through a load or through some sort of device. In this case, no voltage is used until we pass through a resistor. So we haven't used any yet, haven't used any yet, haven't used any yet. So our voltage is still 12 volts at this point. And even when we go through the dividing path, we still have not actually passed through a load. And so you really still have 12 volts of potential on each side of this branch. And so at this point, before R1, we have 12 volts, and at this point, before R2, we have 12 volts. Let's backtrace our 0 and see if we trace it back to the last point that any work in the circuit is performed. Well, no, haven't done any yet. No, still haven't done any work. And we see that even past this, the last point that any work is done is either moving through this resistor or through resistor number 2. And so we actually get the full 12-volt potential across each resistor. And that's the thing to remember in parallel circuits. The voltage is the same across both branches of the circuit. And that's because until voltage is actually used moving through a load, it remains the same. And so we still have the full 12 volts here and the full 12 volts across this circuit, across this parallel branch, since there are no other resistances in this circuit at all. All right, so it looks like 12 will actually be the value that we'll put in here. So 12 divided by 40 at that point leaves us with 0.3 amps. And so we see that through the more resistive branch, branch 1, we actually have 0.3 amps of current. All right. Well, a quick check of the math will tell us that through branch 2 we should be getting 1.2 amps. But let's go ahead and double check that anyway, just for fun. So here we have 12 volts, again, as the voltage across resistor 2. And so I2 and then times, and R2 is 10. Okay. Well, 12 divided by 10 looks like 1.2 to me. And so 1.2 amps will in fact be the current through branch number 2. All right. Well, at this point we have solved. We know that we know our voltage drop across each resistor. We know the current through each resistor. It is 0.3 amps through the upper branch, branch 1, and 1.2 amps through the lower branch. And then when those come back together, again 0.3 and 1.2 will once again combine to make 1.5. So we know the current at all points in the circuit. We know the voltage at all points in the circuit. The only thing left to calculate if we wanted to would be power. If we wanted to calculate the power, we would say that the power is equal to the current times the voltage. And again, just as we can apply the Ohm's law, V equals IR, to the entire circuit, we can apply the power equation to the entire circuit to know the power utilized in the circuit. Or we could apply it to each individual branch. P1 equals I1 times V1, where once again we would use an I1 of 0.3 and a V1 of 12. And so just looking at that real quickly, it looks like P1 would be in fact 3.6, and our unit for power is watts. And so the power used there would be 3.6 watts. And sure enough, the powers used in each branch should also add up to be the power of the circuit as a whole. All right, well, I will leave you to finish the power for the whole circuit as well as the power through resistor 2. And hopefully this was helpful to you, and that gives you a little better understanding of parallel circuits. Have a good day. Thanks.